we have to discuss with you about the angle of contact. Fluids at rest we are doing, we have discussed about the forces, cohesive forces and adhesive forces with us. In the previous lecture, we have discussed that if I take the water in a container I can take of glass, say, then there are two forces with me. One is the force, cohesive force, that is between the water and water molecules, and another is adhesive force. Adhesive force is between the water and glass molecules, with different type of molecules. This is adhesive force. And if the water molecules, I'm taking the force, that is the cohesive force. So these two forces are there for different liquids. Even if in place of water I take alcohol, again alcohol molecules will have the cohesive force, and alcohol glass molecules will have the adhesive force. Because of the adhesive forces you are using in day-to-day life, you are able to paste one thing with the help of glue. That glue you also call it as an adhesive material. So from there also you can remember the things in your mind. Now what it is that if I'm taking the water in the glass container, then two forces, cohesive forces between water molecules, adhesive forces are between the water and glass molecules. Now the cohesive forces are less than the adhesive forces, then the liquid, it always wets the glass or the container molecules. But if the cohesive force is, and of course in this first case when I'm taking cohesive force is less than the adhesive force, then water or the liquid is going to wet the glass, and in that case the meniscus of the liquid which you are finding is your concave meniscus. And what is angle of contact? Here if I'm making a tangent at the point of contact of, see, this is when I'm taking, of course, when you see water in the container, you see the circular shape of the meniscus. But when you see from the front, then you are able to see the concave. That you must have observed if you put the water in any glass container. Now, angle of contact is, I can find from anywhere wherever the liquid is in contact with the glass. And at that point, I have to draw a tangent. And here, this is the line which is between the water and glass molecule, this line. On the surface, you can find it any point. So what is the angle between these two? That is your theta. And I call this angle as the angle of contact. Similarly, if I am taking the mercury here in the glass container, is again I am taking glass container, and here the cohesive force is greater than the adhesive force. Then the liquid does not wet the glass, and the meniscus which is formed is convex upward. This was concave upward. So circle will be formed like this, of course, convex upward. And angle of contact is always, if I draw a tangent at the point of contact with the line which is inside the liquid, this line. So what is the angle made here between these two lines? That is your theta, that is the angle of contact. So angle of contact, if I want to define, that is the angle between the tangent to the liquid surface at the point of contact and the solid surface inside the liquid. So this you have to keep in mind, that solid surface is taken inside the liquid. And with that, if you and at the point of contact, you are making the tangent. And then if you make the angle, that is your theta. Here, of course, you can see theta is acute for the water. If I have taken theta is less than 90. It means acute angle. And here if I have taken the mercury, then theta is greater than 90. It means obtuse angle is formed. So angle of contact is obtuse for mercury. Sorry. Angle of contact theta is obtuse for mercury, while it is acute for water. So this, for the liquids which wet the glass, theta is acute or less than 90. For the liquids which does not wet the glass, theta is obtuse, or I can say greater than 90, but of course less than 180. Now if I have taken the liquid is like that your adhesive forces and cohesive forces, they become equal. Like if I put the water in some silver container, then what is found that adhesive force is equals to the cohesive force. And in that case, your theta will be equals to 90 degree for water and silver. So this is the silver container now. So day-to-day life, you can always observe water and glass because they both are available at your place. And from here, only this knowledge further is helping me, that it means my angle of contact depends on what factors. It means what liquid I am taking and what solid I have taken, means container, either it is glass or silver or plastic. So it depends upon both. So it means value of angle of contact, whether it will be acute or obtuse, will depend upon the nature of solid and liquid in contact. Of course, it will depend upon the cleanliness of the surface in contact and what is the medium above the free surface of the liquid, whether it is air or if you have filled some other gas, it will depend upon that also. And of course, it will depend upon the temperature of the liquid also. That also you can observe in your daily life. When you take the hot water or you cold water, you simply observe the angle of contact. Before going into capillarity, you should be knowing what do you mean by a capillary. It is a thick pore glass tube, very thin bore. So bore is very thin, and you have observed, if you have not observed the capillary action, you must have observed, and many of you must have observed the capillaries. These are available in plants. Green linings are there with you. Sometimes if you just observe, when you even take the wall, that some liquid is coming out from these saplings of the plants, that is your capillary tubes are there. In your towels, sometimes you observed small capillaries, thread-like structures are there. And your nib, this when I'm writing with the pen, the nib of the pen from where the ink is coming out, so that much thin it is. Pen, when you write, everybody has observed it. Even you can observe it now, that the thin pen from where the ink is coming out, you can see it is coming in very thin bore. So that thin bore tube, if it is there, that is known as the capillary tube. In the lab, when we work with the capillary tube, we take made up of glass. But in day-to-day life, you are able to observe the capillaries of different materials. What is observed, that if I put the capillary tube, which of course I have shown of different diameters, it means radius are different. Then if I put it in the water or in any liquid, then the liquid is rising above the water level in the container. This is the water level in the container and the liquid is rising up. Now if in place of water I take the mercury, if I take the mercury here and I put the capillary tube, then it is observed that there is some fall in the liquid. It means liquid is filled, mercury is filled up to this level. But if I'm putting the capillary, the level is coming up to this. So little below the liquid level in the container. But in case of water, it is rising above the water level in the container. So this happens by itself. And this phenomenon of either the rise of the liquid in the capillary tube or fall of the liquid in the capillary tube in comparison to the surrounding level, that is termed as capillarity. So capillarity is simply the phenomenon of rise or fall of the liquid in the capillary tube in comparison to the surroundings. And applications, as I have said, you have noted it down while writing. Capillary action can be seen in plants. You can see the capillary action. Even you use the blotting paper to soak the ink. In that also small capillaries are there. In your towels, they are able to soak the water from your body. That is also consisting of capillaries. So liquid can rise in the capillary tube or there can be fall in the level as compared to the surrounding level. That phenomenon I am calling it as the capillary. So in your syllabus, especially they have mentioned the phenomenon for the rise of the liquid. This is of this mercury case I have drawn beforehand just to show that fall of the level is there. With the rise of the liquid in the capillary tube. Similarly, if I want, I can find for the fall of the liquid, that is descent formula. But in your syllabus, they have specially mentioned with the ascent formula. Ascent formula means the formula which we want to get for the height above the liquid surface when there is rise of the liquid. So my question is to find the expression for this H, height of the liquid. So that also you can observe that when you do the experiment, even in the chemistry lab, they ask you to measure the lower level of the water because it is concave. And if I consider the whole thing, means if I make, this is the capillary tube and it is rising up to this level, a little bigger in size I am making. Then here up to this height we measure. Again, I am able to measure up to this height. But liquid is there in this also. Here also liquid is there. That is equals to R by 3 volume. So that volume we may ignore even. And there are two methods with me to find the height. One is by taking the reaction forces, means the upward force, and then the downward force. Downward force is the weight of the liquid and upward force is the thrust or the force which is acting in the upward direction. Another simple method is I can see that the liquid will rise till the pressure at these 2 points, they are in equilibrium. So for keeping the pressure, of course, excess pressure is always on the concave meniscus. As we have discussed earlier, that if I take a liquid drop, then the excess pressure is coming from inside, means on the concave side. So excess pressure has to come from this side. And so the pressure here will be equals to, if P is the pressure above the surface, then below this surface it will be P minus the excess pressure. And excess pressure we have derived, that is for liquid drop, it is coming 2 sigma by R, where R is the radius of this circle which will be formed at the meniscus. And we are getting the concave meniscus because I am taking the water, and capillary tube is made up of glass. When we do it experimentally, we take the capillary tube made up of glass only. R is the radius of curvature of the meniscus, capital R, while small r is the radius of the capillary tube, which I can find experimentally by using the traveling microscope, from where I can see the small objects, because otherwise there is no other way to find the radius or the diameter of the capillary tube, because the bore is very thin. I can't find its diameter with my naked eye. So I will be using the microscope to find the diameter. Theta here is the angle of contact of case from here, and pressure, as I have said, on concave side it is more, so excess pressure is 2 sigma by 2, and this diagram you can take, this is theta, then you can write this angle also is theta. So cos theta will be equals to cos theta will be equals to small r upon capital R. From there you can find the value of capital R in terms of angle of contact. And this value of capital R you can put in this formula for the excess pressure, which is sigma upon R. So capital R you can replace by small r upon cos theta. So you are getting the excess pressure which is coming out to be 2 sigma cos theta divided by small r. But when it has to attain the equilibrium, it means that should be equals to the pressure because of this height of the liquid. That height of the liquid is h. So I can put this value equals to rho g h. And by simply rearranging, you get the formula for the height of the liquid, that is h, it is equals to 2 sigma cos theta divided by r rho g. Where of course sigma is a surface tension, you all know. Sigma is surface tension, and here's rho is density of the water. Density of water or the liquid. Here I have taken water, so I will write it as water. But of course, if I take the whole volume of the liquid, then this height will be equals to 2 sigma cos theta upon r rho g minus r by 3, just small liquid which is there in the small area which I have shown you. So that part we may ignore when we do it experimentally because it is quite small value of the liquid. So you will be simply remembering this formula for the height, that is h equals to 2 sigma cos theta upon small r rho g, where small r is the radius of the capillary tube. So from here you can see that h is inversely to r. So if the diameter of the tube is more, height of the liquid rising in the tube will be less, and vice versa. So if I am taking capillary tube of small diameter, then it can rise to the better height. And if the diameter is more, like in your straw, it cannot behave like a capillary because diameter is quite more. So height will be less. Capillary tube with me which is of insufficient height. It means this is the liquid I have taken and have filled it in the glass container of this water, and I'm putting the capillary tube in it, which is having the height less than the liquid has to rise. It means liquid was to rise up to this height, but my capillary tube is having the length or height is less than the water rise. So what happens experimentally also it is observed that the meniscus diameter or the radius it increases, but liquid never falls or it comes down from the capillary tube. So even if I take the capillary tube of insufficient height, the liquid meniscus will get adjusted. And that can be proved mathematically also, because I have taken the formula, derived it for the height of the liquid H, that is equals to cos theta r rho. I have seen small r upon capital R, that is equals to cos theta. So I can replace this r upon cos theta by the radius of the meniscus. So capital R is meniscus radius. And from here you can write HR, that is coming out to be 2 sigma upon rho g. Now sigma surface tension of the water is constant at a given temperature of this. Rho, density of the water, is also constant, and G, acceleration due to gravity, is constant. So HR becomes constant. So if H is less, then R increases so as to keep the product of H and R constant. So it means if height is insufficient, then the meniscus of the liquid will be adjusted and liquid will not overflow. This point is to be noted. Now, because you can get the assertion reason type questions also, and they may ask you that both the statements are true or one is true and they are correct. So they can write the various questions on this way also. Options will be written whether both are true or both are false or one is false or reason is correct for the given assertion. So you will be choosing from the correct option, and you have to read the statements for such questions very carefully. Like here I have taken one assertion reason type question for you. That is, assertion is the machine parts are jammed in winter. You must have heard this, and it is true also. Second, they are saying the reason for this, that viscosity of the lubricants used in machines increases at low temperature. So when the temperature is low, what is happening to the viscosity of the liquids? Because we have done this variation for gases, it is a direct relation, but for liquids it is having the inverse relation. So it is inverse relation. Yes, this is also true. Now third thing, you have to see whether it is the correct reason for the given assertion or not. So of course here also machine parts are jammed because of the change in the viscosity of the lubricants, and so that is explaining correctly. So I can say both the statements are correct and reason is giving the correct explanation for the given assertion. So these type of questions also you have to practice for different chapters of course. Keep things up to this for today. Thank you everyone.